Okay, my name's Curtis Whitson. I'm going to go through and illustrate the use of a video created by using the tablet type system on Windows with the Windows Journal and the Camtasia system for recording video and voice. And we're going to talk about gas material balance in this short lecture. And the starting point for the gas material balance, and in particular the straight line gas material balance, is basically the gas PVT equation, sometimes referred to as the real gas law. And this states that the pressure times the volume is equal to the number of moles times the universal gas constant times temperature in absolute units times the so-called deviation factor, or the Z factor. And basically the assumptions going into the normal straight line gas material balance is that the volume, which is referred to as the hydrocarbon containing part of the pore volume, is a constant and remains a constant during depletion. With that assumption, together with the fact that the Z factor is a function of both pressure and temperature, we assume that the reservoir temperature is constant. And the number of moles remaining in the reservoir at any given time is equal to the number of moles initially in the reservoir minus the number of moles that's been produced. We then introduce some terminology for the surface gas volumes, which are measured instead of moles. Actually, you're metering moles instead of volumes, but they're reported as standard gas volumes. And we have the general relationship that gas volume at standard conditions is equal to the constant R TSC over PSC times the number of moles. And this constant here, of course this comes from the ideal gas law, this constant here is 379 for field units of standard cubic feet per pound mole, or for traditional metric units 23.64 standard cubic meters per kilogram mole, sometimes written kmol, and standard conditions are defined as 1 atmosphere or 14.7 psi and 60 degrees Fahrenheit, which is basically 15.56 degrees centigrade. That's our definition of standard conditions. The relationship now between standard gas volume and moles is here stated. So the initial surface gas in place is, of course, related to the initial moles in place times this constant, say 379 for field units, and the SB unit or symbol for initial gas in place is G, and the cumulative gas produced is written GP. So this is the cumulative surface gas produced. And of course, this is related with the NP, moles of gas produced, again, times the same constant. So we're going to make use of the terms G and GP instead of moles. And together with the assumptions that we have a constant hydrocarbon pore volume, Z factor is expressed as a function of pressure and temperature. The temperature is assumed constant. And we then arrive at the so-called straight line gas material balance, written as P over Z equal to the initial P over Z times 1 minus the basically recovery of surface gas. This term GP over G is effectively the recovery factor of the surface gas. And that's our straight line material balance equation. And graphically, of course, this is traditionally plotted as cumulative gas produced on the x-axis, and P over Z, this is average reservoir pressure over the Z factor at that average reservoir pressure, and we start at the initial values, P over Z I, at 0 gas having been produced, and this results in a straight line. And when we reach abandonment at 0 psi, we have the initial gas in place. So this is the straight line graphical representation of the same equation. So at this point, we're going to basically see that the cumulative gas produced is related with the PVT properties Z factor. This is being the assumption that there's no change in the hydrocarbon pore volume up here. Now, what does this really imply? In reality, what we have is a gas volume in the reservoir, and that's always associated with some amount of water. And the water that's always there is, of course, connate water. This is our water. So we've got connate water. And then we usually have some form of an aquifer, basically an external water source. And then we also often have, but we often neglect, an internal interbedded water source. Basically, it's usually found in shales that are interbedded with the sand or dirty sands, and we'll call this non-net pay of the reservoir. This is interbedded water, and all of these waters are associated with the hydrocarbon pore volume. And in general, when the pressure decreases, these different sources of water will expand. Of course, the pore volume itself will contract as pressure drops, but we make the assumption that no water is encroaching into the hydrocarbon pore volume, and that the pore volume itself is remaining constant as pressure drops. Neither of these assumptions are particularly good. Now, let's now look just at some of the characteristics where, in fact, this assumption is implied. Most equations make this assumption. So we're going to take a look at the behavior of the material balance and how it's calculated from this simple equation of state. So all we really need is the PVT properties of the gas, which is the pressure and the Z factor at that pressure. So let's look at creating basically a gas material balance spreadsheet calculation, and we'll look at some of the characteristics of a gas material balance. And to do that, we need to get the Z factors, and now I'm going to make use of a pre-constructed spreadsheet that uses the Standing Katz Z factor chart as given by the Yarborough equation. It's a BWR, Benedict-Webb-Rubin type equation of state. And of course, the gas Z factor depends on pressure, temperature, and the composition of the gas. And the composition of gas can be input as molar amounts, or it can be approximated by the specific gravity, which, let's say we use 0.75, a fairly light gas. And there are certain correlations that give us the approximate pseudocritical temperature and pseudocritical pressure, which are being estimated here, not from the composition, but from the gas-specific gravity. And with that, we then can calculate the pseudo-reduced pressure and temperature, and this is the calculation. It's using a Visual Basic routine, ZFAC, which is the function of the pseudo-reduced temperature in cell B11, 1.7, and the pseudo-reduced pressure, which is shown here. And this Visual Basic algorithm is basically shown here, and you can look at that sheet later. We'll just basically borrow the numbers from this spreadsheet and move it into our material balance spreadsheet. This is our pressures, and the Z factors, will copy that over to our other spreadsheet, paste special, and just take the values. And now we have these pressures and Z factors, And from the equation that we just derived here, we can construct this straight line material balance. So we first create the column P over Z. Has the same units of bar. And we go down here. And then what we're going to do is we're going to do two plots. We're going to plot, first we have to calculate the G divided by GP. And we'll plot that in percentage, calculate it in percentage. And we calculate GP over G by rewriting this equation as 1 minus P over Z divided by the initial P over Z. So that's a simple calculation here. Divided by the initial, and we assume that 1,000 bar, which is 15,000 psi. We have a field in Norway at that pressure, the Kristen field. A little over 900 bar initial pressure. And we'll then calculate these. This is in fraction. We'll give this in percentage. And now we've got the percentage of basically the recovery factor of gas shown here. And we'll make a plot of that versus P over Z. Insert the chart. Use the XY scatter chart. And we'll include the axes. And we'll create a new sheet. This will be our gas material balance sheet. And we'll clean it up a little bit quickly here just to make it more readable. And basically publication quality takes just a few extra seconds. We'll get rid of all these extra digits we don't need. We'll make it into a little bit larger font. The entire use 14 or 16 point font so you can copy straight into publication. We'll make it full size and use the circles, open circles, and go ahead and put the straight line through it. Now basically we have a plot here that we can copy straight into. We don't have any labels, so we need to get some titles in there. We're plotting on the x-axis the gas, basically the cumulative gas recovery, GP over G in percentage, and the P over Z in bar on the y-axis, except that's not actually what we're plotting. We have to go in and change the series here, plotting E versus D instead. Yep, one more time. Okay, so now we've got our P over Z plot and straight line as you would expect. Now, one of the interesting things about high pressure reservoirs is that most people think that if you deplete half the reservoir pressure, you get half of the gas recovery. This is not the case for high pressure reservoirs, and we'll show that by example. Plotting together with this, we'll make maybe a new plot here. We'll copy this and we'll add to the figure a plot of pressure versus cumulative production together with the P over Z. Maybe we'll just substitute and plot only pressure versus cum. And in that plot you'll see that because of the Z factor effect that you get a lot less recovery after having depleted the reservoir to half its pressure. We'll go in and just plot here instead of the P over Z, we'll plot simply the pressure. We'll rename it, basically just pressure. That was obviously not the right thing I plotted. And we go in here, we've got C instead of D, we want to plot pressure. I want to plot here. pressure, no, we're plotting cum on the x-axis. Let's see what I put. On the x-axis we got recovery factor. On the y-axis we want to plot pressure. There we go. Okay, and now what we see is that after reducing from 1,000 bar to 500 bar, we've only produced 21% of the gas instead of what you usually would expect would be 50% of the gas. That's all because of the Z factor, and this is very traditional of high pressure gas reservoirs. So that's one of the characteristics that we need to keep in mind, and you don't see it on the straight line curve because it's very difficult to see on P over Z what's half of the reservoir pressure. Here you see it very clearly, 21%. Now let's return to the violating assumption that you have no water encroachment and no pore volume reduction. This assumption right here. Now we're going to relax that, and for the simple case where we assume that all of the water available and in connection with the hydrocarbon pore volume will respond instantaneously as the pressure in the hydrocarbon pore volume drops. And that's referred to as a pot aquifer model, and it's applicable for small aquifers, and it usually requires a relatively high permeability. But that's just an assumption. We'll just look at the characteristics of what does the water encroachment into the hydrocarbon pore volume do to affect the material balance behavior. And there's a very simple modification of the straight line material balance to deal with that pot aquifer model. Okay, and basically it looks like this. We get P over Z times 1 minus an effective cumulative compressibility, we'll talk about that in a second, times initial pressure minus the current average pressure. So this is kind of a new term for material balance, and that's equal to the same as we had before, the initial P over Z times 1 minus recovery factor of the gas. And at this point, we're going to look at this CE term, and as defined by Fetkovich et al. In the early 1990s, this is equal to the formation rock compressibility plus the water compressibility times the connate water saturation plus a term M, and this is related mainly to the aquifer volume size. We'll talk about that. C of F plus C of W, total compressibility of aquifer, divided by 1 minus connate water. So typically we might have something in the range of 25% connate water. Formation and water compressibilities are usually quite similar. Let's say 5 10 to the minus 6th inverse psi, and M is effectively the aquifer volume divided by the hydrocarbon pore volume. And typically values of 1 to 5 are what we see for reservoirs that the pot aquifer assumption is valid. So we basically say that there's 1 to 5 times aquifer volume to the hydrocarbon pore volume. And if we put these numbers together and come up with some kind of effective compressibility, let's just do that in our spreadsheet. We'll add basically the SWC term, the CW, we'll say that's equal to the CF, and we've got the M and then the CE term, and we've got we need 1 over bar here for our units, and we'll put in a value of 3 for the M, which is 3 times the hydrocarbon pore volume, 0.25 for our make all these in red since we're inputting them. Make this okay, the 5, okay, now 5 10 to the minus 6th in 1 over psi we have to multiply by 14.5 psi per bar to get in 1 over bar. And then we go down and we use the equation that was given here, basically the formation plus the connate water times compressibility. So we use this equation to calculate the effective compressibility, and we get that's CF plus CW times SWC, and then it's times or plus M times the sum of these, basically that plus that again, and then divided by 1 minus the connate water saturation, and we need another, yeah, so we got the parentheses to fix that for us, and then we'll put these in units we're familiar with scientific. So we've got 6.7, 10 to the minus 4th effective, which basically is a factor of 10 larger than the formation water compressibility, and that's so that effective compressibility is 10 times what you would expect for water and formation compressibility. So now let's look and see how this will affect the material balance, the pressure versus cume and the P over Z versus cume plot, including this pot aquifer. So now we're going to have to solve this equation for GP over G will be 1 minus, and now we've got the P over Z term, times this entire 1 minus CE PI minus P term divided by P over Z initial. And we'll calculate a new column in the spreadsheet here, which will basically, this is for our straight line, or let's say hydrocarbon pore volume being constant assumption, and this is for our pot aquifer model. And we'll say this is equal to, let's say that equation there, be 1 minus, and then the P over Z is the same here, times 1 minus the effective compressibility, that's up here, times the initial pressure, which is over here, minus the actual pressure there, close the parenthesis, and then we need to divide that by the P over ZI initial here, and that, I have to be careful of the units here, or the parentheses. That parenthesis gets us there, and that parenthesis there, and that there, and then we'll make it 100%, or make it into percentage. Yeah, that was all right. 100 times parenthesis. Okay, so now we've got the recovery for the pot aquifer, and we'll add that to our plots here. We'll add another plot. We'll call this our straight line hydrocarbon pore volume constant result, and then we'll be plotting the same pressures here, but for the aquifer, this is our pot aquifer, and we'll be plotting here on the y-axis the we'll plot the same y-axis, but we'll change the x-axis to be this column. That, and there we get our very nonlinear pot aquifer very typical pot aquifer type behavior. You have a much slower pressure decline, and it turns around and drops. So you basically have a lot more energy in the reservoir at any given time. So in this case, we can add the figure to the other as well and see how it affects the pressure versus cume plot. Do the same kind of plot here. Just say the straight line, and then we'll add in this case we'll plot this inverse. No, that's not pot aquifer. And And interestingly, it basically cancels out all of the z-factor effect and gives us more or less a straight P pressure cume curve. Of course, if we change the amount of water that's in the system, this number here, if we change it to 0, meaning that we have no associated water, of course we get the two curves should be basically identical. Why they're not, I'm not sure. Oh, that's because we basically have according to the equation here, even though m is 0, we still have the rock and connate water compressibility. So what you see from this figure with no aquifer associated is the effect of only connate water and pore formation compressibility, which is actually significant. It's not negligible. So that small amount of water and pore compressibility still has an effect. And to get rid of that, we would have to actually put the compressibility is equal to 0. So that basically gives you a tool to look at the effect of aquifer size, formation water compressibilities for a simple gas aquifer type model. And I think with that, we'll conclude the presentation. I don't think there's anything else left here to look at.